how can we think about when a nucleus is vibrating and rotating? So first we just need to think about vibrations. As we discussed earlier, a nucleus can be estimated as a liquid drop. If we think about a liquid drop vibrating at a high frequency, then what can be the estimate we can say is that, well, on average it's a spherical nucleus, but instantaneously the shape is not spherical. And how we label this is by saying, well, in this instantaneous shape, for example like this, we find a point on the instantaneous surface which we call R. And because this is an instantaneous point, it depends on time and its position on the surface. So these angles come from its definition. This length we call B, and this length we call A. Now we have an expression for R, which says this here is a spherical harmonic. The alpha is the amplitude. And the fact that alpha is dependent on time means there's a vibration. If alpha was just a constant, we would only have rotation in this case. R0 is our good old estimate of just this expression for the radius of the nucleus, where R0 is 1.2 femtometers. Now, how we describe these vibrations is also, we know that they're quantized. So we say that the nucleus is producing vibrational phonons. And these are essentially a particle which are used to describe these vibrations. And we say that they have an angular momentum. And in this case it's not L as we're used to, but lambda. Different types of vibrations depend on this value of lambda. So for example, if lambda is 1, we have a dipole vibration. And if I'm just going to draw this, it looks something like this. It is our nucleus where the center of mass has actually been displaced. And this is not caused by the internal nuclear force, because we know that that only causes it to vibrate around its center of mass, but in this case there's actually a displacement. So we're not too worried about this one in terms of vibrations. For lambda equals 2, we have a quadruple vibration. Now this one we're actually very interested in. And it looks something like this. Again, this is our equilibrium shape of the nucleus, and an instantaneous shape is like this. So here the vibration is clear, And what we say here is that 1 unit of a quadrupole vibration, we describe that as a quadrupole phonon. So these are essentially what's produced by this vibration. If we have lambda equal to 3, we have an octupole vibration. And this also happens around the center of mass in a similar way. So again, we have the equilibrium shape. And the instantaneous shape is actually a bit difficult to draw, but it's something like this. We're mostly concerned about this one and this one because they're actually causing the changes in the vibrations. Now what happens due to these vibrations is that actually there's some excitations in the atoms, or in the nucleus, sorry, and the nucleus is changing shape over time. So in the atom we see something like this. So this example is for an even atom, which means we have an even number of protons and an even number of neutrons. So in this case, we have these excitations which go in steps of 2 in terms of the nuclear states. And as you can see, these steps of 2 means we're actually dealing with this one. And so these excitations are due to the first phonon, and these excitations are due to the second phonon involved. We know that the energy of a phonon is equal to h bar omega. So in this case, here, the energy is h bar omega. And for the second phonon, we actually have 2 h bar omega. So this is the energy spectra of the atom. No, of course, of the nucleus, sorry. Now the nucleus can also have different shapes than an equilibrium spherical shape. For example, we define it in terms of around the z-axis. If we have, well, at first this shape. So from our previous picture, this means B is greater than A. We call this prolate shape. And actually we define this thing called the electric quadrupole moment, which is an intrinsic property of the nucleus, and in this case this quadrupole moment is greater than 0. We can also have, of course, just our regular spherical nucleus. Here we have B equal to A. This is just spherical. And our quadrupole moment is 0. Lastly, we can have a shape which looks like this. And of course now A is greater than B. We call this oblate. And Q0 is of course less than 0. Now we want to think about nuclear rotations and what effect that has in the nucleus. Well, it just so happens that in order to observe nuclear rotations, quantum mechanically, we have to have a nucleus which is deformed, so we can't observe it for spherical nuclei. So need deformed nucleus to observe this rotation. And if you think about a droplet of liquid rotating, then of course this will also cause some changes in the shape over time. So we have this rotation. In quantum mechanics, we can define the energy of a rotating object as being h bar squared where this J is the moment of inertia and I is the angular momentum quantum number. So then for different values of I, we get different rotational energies. So that means in a nucleus, when we're exciting it to higher values of angular momentum, then we get this splitting of the energy levels. And it turns out actually that the rotational behavior of a deformed nucleus like this is sort of between a rigid object and a fluid. If we compare to the moment of inertia of a regular rigid object, then we have the moment of inertia of the nucleus is in between this rigid one and the moment of inertia of an ordinary fluid. So we can make a conclusion that the nucleus is actually it has this consistency, or it acts as if it's sort of made of this material that's between solid and liquid, and we can think about it actually kind of as an egg.